Hello and welcome to our program, Astronomy for Everyone. For our final show of 2013, we're going to take a little bit different approach to how we're structuring the show. We're going to start out with an update from our May 2013 show on the Mars Curiosity mission. And then after our break for Term of the Month, we'll be back with questions from you, our viewers. So this should make for a very interesting program. But as I said, we're going to start out first with the update on the Curiosity mission to Mars. And with me here in the studio is Stephen Whitty. Stephen.
Good to be here. Thanks, Don.
You're welcome. I know you did the original program on Curiosity back in May, so I thought it only fitting that you bring us the update.
Yeah, well, Curiosity has a ton of instruments, and it was even tough to get through all of the instruments in an hour. We're not going to do that. We're going to just talk about the science that has come out of the mission, what was written up, what's been published even on the web somewhere, whatever I could find. So the first thing is that the mission objective, this is the big news, the mission objective, is Mars habitable? Well, the Curiosity rover has certainly discovered a place that was wet, there was a stream, there was fresh water, it was a very benign environment. Life could have formed there, at least the conditions were right. Everything is all set up for that. So the mission objective, which was land in a spot where you could find something like this, that's been done. And in fact, it was done very early in the mission. Quite a ways, maybe 6 months into the mission, the drill was finally used at Yellowknife Bay, and what was extracted was some clay materials, and these clay materials can only form in the presence of water. And so this place certainly was wet, and it was wet enough to form not just a little bit, but quite a bit of clay. Yellowknife Bay hasn't been dated yet, so we don't know exactly when this happened, but we think that this is early in the history of Mars.
And these are, as you mentioned, the images from that point where those samples were extracted.
That's right.
Okay.
That's right. So just four scientific papers were published at the 1 year mark, so this is in August. At the 1 year mark, they were all published in the scientific journal called Science, which is a very respected journal.
Indeed.
4 papers is not a lot for a mission that has tons and tons of instruments all over it. It has dozens of cameras, it seems. It seems like not a lot, but really what is going on is that we spent an entire year doing engineering checkout of these instruments and calibrating them, making sure that they're telling us what we think that they should be telling us. So now we're basically ready to do the science. And then the other thing is that we didn't land in the spot where we're going to collect the data. That's Mount Sharp. That's quite a ways away from here. But anyway, the 4 papers.
Yes.
The first one happened during the cruise to Mars. There's a radiation meter, and a paper came out, and it said that a round trip to Mars, like if you had a human mission to Mars, a round trip to Mars, the astronauts should expect to receive 660 millisieverts of radiation. So most of us, I don't, most of us don't know what this means, so I looked this up. 50 millisieverts, so this is a 12th roughly of what the astronauts would get. 50 millisieverts is the radiation dose allowed to a radiation worker, so somebody at a nuclear power plant, over the course of an entire year. 1 year, 50 millisieverts. It's actually not too much higher than background radiation that you'd expect just living in your house. At 100 millisieverts, that's the lowest amount of radiation that has been positively identified with an increased risk for cancer. So 100 millisieverts you can think of as cancer. So we're still a factor of 6 to go to get to the astronauts. So the astronauts would be getting some risk of cancer. At 2,000 millisieverts, if you get it more or less all at one time, that's radiation poisoning. You should go to the hospital. You're going to feel sick.
This would be something similar to the atom bombs in Japan at World War II?
Possibly. I don't know that for a fact, but possibly. There are certainly people who survived. In fact, there are like 4 or 5 guys who survived both Hiroshima and Nagasaki. They were in the blast for both times. Not very lucky guys, but you know, it happened.
But certainly this is a very almost lethal dose.
Exactly.
Yes.
Exactly. At 4,000 millisieverts, you could call it 4 sieverts, but 4,000 to 8,000. At 4,000, your likelihood of dying on the spot is quite high. If you get medical attention right away and everything lines up right away, you might survive. But at 8,000, no, wrong.
Okay.
No, that's it, death.
So based upon what they've learned with Curiosity, an unmanned mission, if we're going to send people up there, we're going to have to do a much better job of shielding them from this radiation?
The radiation shielding has to get better. In my opinion, 660 millisieverts is higher than I'm comfortable with. I wouldn't go. I personally wouldn't go. And I'm not comfortable sending somebody.
Okay.
But radiation shielding is something that is, we know materials that can do it, and we have to have the will to design it in and make it happen.
Okay, what's next?
Okay, so the next paper, there's this outcropping of rock, and it has these pebbles embedded in it. So it's a conglomerate, they call it a conglomerate. And these pebbles that you can just kind of barely see in this picture, these pebbles are rounded, and Curiosity could see that. The photos that they took, actually this photo that, you know, in the full resolution, shows that the pebbles are rounded, and they're rounded the way that you would expect them to be rounded if they were in a stream and they were getting pushed down the stream.
Much like we would see here on Earth.
Exactly. And they had to have gotten pushed down the stream a couple miles, and the water had to be somewhere between knee-deep and waist-deep. So
to have enough volume of water to have the force to push them, to round them.
That's right. And you compensate because Mars' gravity is lower and that sort of stuff. You know, we get all of those ducks in a row.
Okay.
Right? So that's the paper. And then the final 2 papers are both about isotopes of different elements in the atmosphere of Mars. And so these things are like carbon, oxygen, hydrogen, and argon. And they did a bunch of things with these. One is that they compared the ratios, like you'll have 2 isotopes of argon, and they compared the ratios between those in the atmosphere today at Mars and those in the Martian meteorites that we have here on Earth. And they line up very well, and so this gives us even better confidence that these rocks are in fact from Mars, that they have to be. But also, you can do things, they did things where they said, okay, so we know that the atmosphere of Mars is thin now, but we had liquid water flowing on Mars at least, and we think maybe a couple billion years ago, 4 billion years ago. We had flowing water, so we must have had a thicker atmosphere. Right now, water on Mars, it sublimates into a gas. It doesn't even...
you don't have enough vapor pressure, atmospheric pressure to hold it in as a liquid.
No, it doesn't freeze, it just goes straight to air,
Okay.
straight to vapor. But it must have been heavier, more air back then. So they basically characterized how Mars lost its carbon dioxide atmosphere. The carbon and the oxygen separate, the oxygen binds to something in the rocks. We see that in the rocks. Mars is red because it's rusted with oxygen, right? And it looks like not only did this start fairly early in the Martian history, it seems to be continuing. And then so then we have so that's the papers really. So then we have where are we going? We're going to Mount Sharp. And Mount Sharp, in this picture, you can see the landing ellipse. And the landing ellipse is like 20 miles the long way, And the distance from, I mean, the dot is where they wanted the dot, and maybe you can't see the dot in the center of the ellipse, but that's more or less where they were aiming Curiosity, and it's pretty close to where Curiosity actually landed. And the crater, this crater, is like 50 miles across.
The Gale crater.
The Gale crater. Mm-hmm. And the mountain is in the middle of it, the Mount Sharp. So it's quite a ways to Mount Sharp. From August to about the middle of September, Curiosity made it close to the first of 5 waypoints. So Curiosity is about 1/5 of the way to Mount Sharp. It's got several more months, maybe 5 more months to travel before it gets to Mount Sharp, and that's where it'll finally slow down and do some real science. That's where, that's the place that they wanted to go. That's where they have to go. Opportunity, as of our recording, has the record for 1 day of driving, and that's 170 meters. Call it 170 yards, it doesn't matter. Curiosity's longest trek is 141.5 meters, so it's not as far. Opportunity has software that has been checked out for a much longer time. It's been on Mars for 9 years or so, and we still need to check out the Curiosity software. But Curiosity's wheels are twice as big. It has a big power source. It can certainly drive every day. It can certainly drive during the winter. It won't be driving at night, I don't think. It does do work at night. It will be overtaking Opportunity's record anytime now.
And any final thoughts here on some of the Curiosity?
And then finally, Curiosity didn't detect methane on Mars. And that was expected because we detected methane on Mars from ground-based telescopes on Earth. And not seeing it could mean that it disappears faster than so it doesn't circulate all over Mars. But for whatever reason, there doesn't seem to be any methane where Curiosity is.
Interesting.
Yeah.
Well, I hope that our viewers have enjoyed this update on the Curiosity mission. We'll probably do another one sometime in 2014 to bring you the latest updates on that mission. We're going to take a quick break. If you'd like more information, please visit our website, the address of which is down at the bottom of your screen. And right now we're heading to Term of the Month, and after that we'll be back with some of your questions.
The term of the month for December 2013 is binary stars. So binary stars are two stars that are orbiting each other. Really, they orbit a point which is sort of the gravitational center called the barycenter. This is what a pair of stars looks like in the sky. You have 2 dots that are really close together, but some binary stars are so close together that you really can't separate them from each other, even in a telescope. So this one obviously can be separated. You get 2 stars, they're really close to each other. There is a pair of stars that are a binary pair that you can see with your naked eye in the Big Dipper. It's easy to find. It is the second star from the end of the handle of the Big Dipper. And the stars are named, they're separately named, Mizar and Alcor. They orbit each other. They also are each binary stars in and of themselves. You can't tell that, but each of them has a companion. So there are really 4 stars there. And that is Term of the Month for December 2013.
Welcome back. At this part of the show, we're going to take some time to answer questions from you, our viewers, that you've sent to our email address over the course of the year. And we're going to start in with the first question, which is, what is adaptive optics?
All right, adaptive optics. Now this is a solution to a problem that telescopes have, which is that we live on a planet that has an atmosphere. I'm actually quite fond of the atmosphere, so instead of getting rid of the atmosphere, what we're going to try to do is we're going to try to see through the atmosphere in a way that's steady, right? So,
in other words, get rid of that romantic twinkle that poets talk about.
That's right. The stars twinkle, and that's because they move around because turbulence in the air sort of makes little lenses kind of at random.
It's sort of like looking at pebbles at the bottom of a fast-moving stream.
Exactly,
Right.
exactly. So in professional telescopes, they've got a really quite expensive and complicated system. But basically, you've got your image, which would be, if you imagine it, would be a flat image. Mm-hmm. And then after it goes through the atmosphere, it's got all kinds of waves.
That we can see right here in the image.
That's right. Well, yeah, so just above the, you've got the purple bit that's the atmosphere, and then you have the wavy image that comes into the telescope. So after it goes through the telescope, you still have, it's smaller, but you still have the waves, and it's still degrading the image. So what they have is, the big observatories have a bright star that they actually put in the sky using a laser.
Yeah, just because you know the position of it,
And they use a camera on this laser spot, and from it they can deduce how the image has changed. And they've got a mirror which has 1,000 or more actuators on it, and each of these actuators can push on their little bit of the mirror to change the shape of the whole mirror. And then, so the light hits that mirror, and this new shape that has been computed is opposite the shape of the wavefront that comes in, and you get it flat again, and that goes to the camera, which then puts the photons, remembers the photons, detects everything, and makes the image.
I understand that we have something like that for amateurs.
Yes, they do, but amateurs don't have millions of dollars. So in the a little over $1,000 range, there is a diagonal mirror that can move on two axes. So it can move sort of this way, and it can move sort of this way. And what it does is there is still effectively two cameras. So there's a camera that is looking for a bright star in the sky, and what the computer does there at 100 times per second instead of 1,000 is it points the mirror so that that star is going to be in the same part of the image at all times. And this does quite a bit of what the adaptive optics at the professional level does, but it does it cheaper, and it does it for the amateur. It's actually pretty good. It actually sharpens up the image pretty well.
Good. Our next question is, what causes sunspots? Now, the sun is a very dynamic star, a lot going on there. The nature of the sunspots are really magnetic fields.
That's right.
Yes.
So the magnetic fields come from, well, all of the material on the sun is hot enough to be plasma. So plasma, it's ionized, it's electrically charged.
An ionized gas, yes.
And moving electric charges, because it does move, it boils and stuff like that, moving electric charges produce a magnetic field. So you're going to have magnetic fields. Mm-hmm. So what happens is you have these convection currents, and you get a magnetic field generated that goes up to the surface, and then it goes out in a loop. Now, the magnetic field will be either a north or a south polarity. I hear that the solar scientists don't talk about north and south, they talk about positive and negative, just so that you don't confuse it with Earth's north and south. It has nothing to do with north and south.
Right.
So they talk about plus and minus. Anyway, so you have like a north pole coming out of the sun, out of the surface of the sun in one spot, and then you'll have another spot where you'll have the opposite pole, so maybe a south pole, and you get a magnetic loop that connects the two. Well, where the magnetic field lines go through the sun, it shuts down heat transfer right at that spot, so that spot is a little cooler than the rest of the sun, so you get a dark spot. That is the sunspot.
And being cooler, it does appear darker.
It does
again,
appear.
because the temperature is just like metal.
That's right.
The cooler it is, the darker the reds versus the blue or blue-white colors. So.
Yeah, so it's still quite hot. It's still many thousands of degrees, maybe 5,000 or 6,000 degrees instead of 7, right?
Exactly.
So it's still quite hot.
Our next question is the rings of Saturn. Are they solid or not? And what exactly are they made of?
Okay, well, the short answer is that they're made of ice, and a lot of it is water ice. So how big is the ice? And it turns out that radio experiments with Cassini, the spacecraft currently orbiting Saturn, has told us that you get anything from as small as grains of sand to bigger stuff, you know, things you could hold in your hand, a bread basket or something, but all the way out to the size of a house. So they have they vary in size like that.
But the rings themselves, while they're over 180,000 miles across, they're not very thick, right?
That's right. So they're the size of the orbit of our moon, right? So they're huge, but they're very thin. They're only maybe 30 feet thick. So it's much thinner than paper would be if it were the same proportions.
So we have these bits of rock and ice all hurtling around Saturn, held in place by the gravity of both Saturn and those shepherd moons that orbit within this rocky and icy debris. And really,
yeah, absolutely. So they've got their own little orbits, and they are influenced by the bigger moons as well.
Well, we hope that we've been able to answer some of your questions. We would hope that in the coming year here in 2014, you continue to send us these great questions. We'll try and work this feature into a show in the future. Stay tuned. Coming up next, we have What's Up in the Night Sky with Stephen Whitty.
What's up in the night sky for October 2013? We're going to start out with the moons, and we have a new moon on October 5th. So the new moon isn't something to see in and of itself, but the sky is darker because there isn't a moon, and you get to see fainter stuff in the sky, especially if you go to you get outside of the city and you get to a darker sky site. October 11th is the first quarter. First quarter is visible in the evening. On October 18th, we have a full moon, and a full moon is visible all night long, sunset to sunrise. This one happens to be the smallest full moon of the year because the moon is at apogee. That's when it's farthest away from the Earth, so the moon therefore looks the smallest. We also have an eclipse, and I'll get back to that in a second. On October 23rd, we have the third quarter, and that's sort of a midnight to morning object. Back to this penumbral lunar eclipse. So in a penumbral eclipse, the moon doesn't go through the darkest center part of Earth's shadow. It goes through what's called the penumbra. And so the moon only dims by a little bit. It dims by about 3%. It's hard to detect, under ideal conditions, it's hard to detect without photography, and then like really measuring it and all of that sort of thing. But in this time around, at least in Michigan, we only get to see this penumbral eclipse from when the moon rises until the end, so we only get to see part of it. And so most of the world can see bits of this eclipse. Africa can see the whole thing from end to end, but we only get to see the last bit. But the moon rises, at least in Michigan, around 5 p.m., and sunset is after 6 p.m. So you'll be seeing this slight dimming of the moon while the sun is up. I think that's beyond challenging. I think people would be hard-pressed to detect the penumbral eclipse, but that is on the 18th. The sun rises at the beginning of the month at 7:30 in the morning, and it sets at 6:15 p.m. By the end of the month, the sun rises around 8:05 and sets at 6:27. This turns out that the nights are getting longer, the days are getting shorter, so we have longer nights, And so you have longer nights to enjoy the night sky. And what I like about this time of year is that it's not yet freezing. You know, you don't have to wear, you don't have to dress up like an Eskimo. You can be more comfortable. So, the Moon, Venus, Mercury, and Saturn. I've picked October 9th for this image because Mercury is at its greatest elongation. That is, it's as far away from the sun as it gets. It's still going to be challenging. It's still going to be low over the horizon just after sunset. But Mercury is kind of a thrill to see if you can really spot it. Saturn is above it to the right. Venus is much brighter, is obvious. And the Moon happens to be in the lineup on this October 9th. So if the weather's good, that's something to check out. Uranus and Neptune are up later. On the 3rd of October, Uranus is at opposition. That's when the Earth, the Moon, that's when the Sun, the Earth, and Uranus are in a line. So Uranus is as bright as it gets, it's as large as it gets. This is Uranus as shown from, as imaged from the Voyager 2 spacecraft, so that's up close and personal. It's a featureless blue ball, and so even in a relatively large Earth-based telescope, it's a featureless ball. You get to see a little disk. But it is really cool to see. And this time of year, you can see it without optical aid if you know where to look. You'll need a better chart than I've shown you on the screen, but it is possible to see it with just your eyes. Mars and Jupiter are after midnight. Mars rises at about 3:30, and Jupiter rises about 45 minutes after midnight. And this is a shot basically at midnight on October 15th, so the middle of the month, so that you can kind of see where they are. Mars and Jupiter are pretty bright, so it's really easier to say, oh, that's Jupiter, therefore it must be Gemini around there, than the other way around. Gemini is pretty easy to spot, though. There are 2 meteor showers this month. There's the Draconids, and they peak around the 7th and 8th of the month. And pictured here is the progenitor comet, Giacobini Zinner is the name of the comet. So the Draconids is not a huge meteor shower. It gives you about 10 meteors per hour, but it can be worth a look. On October 21st and 22nd, the Orionids meteor shower. This is a little bit stronger meteor shower at maybe 20 per hour, but the Moon isn't quite as good in a position this year for this as it was for the Draconids. The Draconids, they're best in the morning, and the Moon will have set by the morning, so you get out to a dark sky site. It's really good. One of the key bits about meteor showers is to dress warm. If you're just lying there and you're looking at the whole sky, you can get cold even in August. So dress warm. The Orionids is the dust from Comet Halley, which goes around about every 76 years. And that's what's up in the night sky for October 2013. Keep looking up. It's the greatest tree show that you can see overhead.